Okay, so here we're asked to find the missing angles. Let's start up over here. What angles have to equal 58 degrees? There are two other angles, actually three other angles here that have to equal 58. Can anybody name one of them? 7 is one of them. That has to be 58 degrees. Any others? 5. And finally, 2. Those angles have to be 58 degrees. Up here, these two are vertical angles. They're formed by the rotation of the lines. If you think of these two lines as lying on top of each other and then rotating to make that angle, this side has to rotate the same amount. Then these two are 58 because if this line were slid up, they would just lie on top of those other two. Okay, so we've got those 58 degree angles. How do we find angle 1 here? Well, this is a line here, so what's that tell us about these two angles? They add up to 180. So 180 minus 58, that's 122 degrees. So what other angles have to be 122? Careful. There's an extra line down in here that kind of messes this intersection up. But we know this one has to be 122. Angle 3 has to be 122. Down here, things get messed up by this second line going through here. However, we do know that since this is a right angle, what does 10 have to be? That's also a right angle. That's 90 degrees. So if that one's 90 degrees, what's that tell us about 6? That's 90 degrees. 6 is 90, and so is 9. So now to find angle 4 here, since this is a straight line through here, these 3 angles have to add up to 180. Or, since this is a 90 degree angle here, that means this side over here has to be 90 degrees. So these two have to add up to 90. Either way, I can look at it either way. So I'm going to do 90 minus 58 is 32 degrees. So this is 32 degrees, so that means angle 8 is 32 degrees. So they all fit together. Any questions off the homework that you want me to go back and go through? You got them all figured out, right? Okay. The hardest part is when they give you a problem like this where there's a bunch of different relationships. I mean, one that we didn't use but we could have was the fact that this makes a triangle here. And in a triangle, the 3 angles of a triangle have to add up to 180. So you've got 90 degrees here, 58 degrees here. You could find that by doing 180 minus 90 minus 58. Gives you 32 degrees for that angle as well. There's a couple like that, yeah. At least 1 or 2. Nope, there aren't any special ones that add up to 45. It's either 90, 180, or for a triangle, it's 180. So those are your 3 relationships. If they add up to a right angle, so this one and this one have to add up to 90 degrees, that's called complementary. And I remember, what's that? The 2 angles are not necessarily the same. They add up to 90 degrees. So if this is 20 degrees here, this one has to be 70. They have to add up to 90 degrees. Or a right angle. And the way I remember that one is you get complements when you're right. So complementary angles add up to a right angle. They could add up to a straight line like this. So these 2 angles have to add up to 180. That's called supplementary. So you have to add up to 180 degrees. So if I tell you that this one here is 125 degrees, this one here has to be 55 degrees. You have to add up to 180. For this one here, a triangle has an angle sum of 180 degrees. So if I give you those two angles, this angle up here is found by taking 180 and subtracting the other two. What does that come out to be? 46 degrees, it looks like, for that angle. Then the final situation we have, oops, is when we have intersecting lines. This angle and this angle must be the same. They're called vertical angles. And there's two reasons why they have to be the same. If you think of this line here is originally lying on top of this one, it rotates to form this angle around this point. But whatever it rotates here, it has to rotate the same amount on this side. So those two angles have to be the same. If this is 34 degrees, this has to be 34 degrees. Now the other reason those have to be the same is because this blue line here is a line. So that means these two angles have to add up to 180. So this is 180 minus 34, or 146 degrees. But this is also a line here, which means these two have to add up to 180. So that's another reason why these two angles have to be the same, because they both have to add up to 180 with this angle here. They're both supplementary to that angle. So those are the four cases for simple angles. They're either complementary, they add up to 90 degrees. Supplementary, they add up to 180 degrees. They're vertical, which means they're formed on opposite corners of intersecting lines. So they have to be the same. Or they form a triangle, so they have to add up to 180. Then the fifth case is if we have parallel lines cut by a transversal. There are 8 angles formed here. But there's only 2 different measurements, 2 different angles. If I know that this angle here is 55 degrees, those other 3 have to also be 55 degrees. These 2 are vertical angles. They're opposite sides of intersecting lines, opposite corners of intersecting lines. These 2 have to be 55 degrees because, as we've mentioned, this line, we split it up, it's going to lie right on top of the other one. So those 2 angles are the same angles. You have to be given one of the angles, otherwise you can't do anything with it. Okay. Well, because these 2 have to be linked together because they're vertical. They're opposite corners of intersecting lines. So those 2 have to be the same, the 1 and 3. But then whatever is here, you just slide it down a notch. This is in the same position here. So this one has to be 55. Think of it as if I took this line out right here, if I removed that line, where would this angle fall? Well, that angle would just fall right down to there. That's where it would land. So now I know this angle and the 55 degrees have to add up to 180 because that makes a line across there. 180 minus 55 is 125 degrees. So that's 125 degrees. That's 125 degrees. That's 125 degrees, and that's 125 degrees. Now, normally on these, like I said, when you have parallel lines cut by transversal, there's 8 angles formed, but only 2 different angles. And normally you can tell which ones are which. Like here, this one is an acute angle, right? By acute, I mean less than 90 degrees. So if I come down here, the 6 is bigger than 90 degrees. It's obtuse. That cannot be 55 degrees. It has to be bigger than 90. So I know that one can't be the same. So all the acute angles have to be 55. All the obtuse angles have to be the 125. Does that help at all? Yeah, it'd be a little more difficult if it was like really close to 90 degrees like that. But still, you can tell that this one's smaller than 90 and this one's bigger than 90. So you know that this one has to match up with all the ones that are bigger than 90. On a test, I won't give you any that are real close. I'll make it like this, where it's obvious which ones are acute and which ones are obtuse. Okay, our new stuff for today. We're going to talk about powers and roots a little bit more, exponents. And we have done things like this. 8 to the power of 3 is how that's pronounced. How would we calculate that? 8 times 8 times 8, which gives us 512. On your calculator, most of you have this caret key here. It looks like that. That's your power key. Others have a key that might look like x to the y or y to the x. Many of your cell phones, if you're using your cell phone as a calculator, have that key. So to do 8 to the power of 3, it's 8, hit the caret key, and 3. Gives you 512. If you recall, when we had negative numbers, if I had negative 7 squared, should that be a positive result or a negative result? It should be positive, because that's negative 7 times a negative 7. And a negative times a negative makes positive. Now you do have to be careful on your calculator. If you just type in negative 7 and then x squared or to the power of 2, it tries to tell you negative 49. Why did it give you negative 49? You have to put parentheses around it. On the calculator, order of operations says an exponent happens before a negative. So on the calculator, this is taking the 7 and squaring it and then putting the negative back in front. So yes, you have to do parentheses around the negative 7, then squared. And it correctly gives you a positive 49. How about like negative 4 to the power of 3? Positive or negative? It's going to be negative because it's to an odd power. Negative 4 times negative 4 times negative 4. If we work it out, negative 4 times negative 4 would be a positive 16, because a negative times a negative is a positive. But then times the next negative 4, a positive times a negative is back to being negative again. So it is a negative 64. You can see the calculator does concur. How about negative 3 to the power of 4? Positive or negative? Positive. Again, we established this before. An even power, the negatives will all cancel out and we'll get a positive answer. That should be a positive 81. And it is. How about negative 5 to the power of 5? Positive or negative? It will be a negative. It should be 3,125. Negative. And it is. Well, we've done powers before. What we want to focus on today is the opposite. We've learned so far that every operation has an inverse. They come in pairs. When we talked about addition and subtraction, we talked about how they are really the same operation. It's just one is going forward and the other one's going in reverse. Well, addition and subtraction are called inverses. They follow the same rules. They are at the same level in our order of operations. And they reverse each other. Somebody give me a random number between 10 and 20. What was that? 13. Perfect. Somebody give me a different number between 10 and 20. What's that? 11. Perfect. If I take 13 and I add 11 to it, I get 24. Well, what do I do if I want to take that 24 and get back to 13? What would I have to do? Subtract 11. So what we see here is if we add 11 to a number and then turn around and subtract 11 from that result, we get right back to where we started. Adding and subtracting are inverses. Adding a number and then subtracting the same number cancel each other out, put you back to where you started. That's why when we solved equations, if we had x plus 9 equals 13, how did we get rid of the 9? We subtracted the 9. Because we started out with x, we added 9. If we subtract 9, it reverses it, takes us back to where it started. Multiplication and division are the same way. So let's say I started out, well, somebody give me a random number between 10 and 20 again. 18. And another one. 12. So if we do 18 times 12, we get 216. Well, if I take that 216 and I want to get back to 18 again, what do I have to do? Divide by 12. So again here, multiplying by 12, and then taking that result and dividing by 12, puts us right back to where we started. Those are inverses. And again, this is why when we had an equation, if I had 4 times x equals 28, x has been multiplied by 4. To solve it, we would divide by 4. It cancels out the times 4 to give us x equals 7. So multiplying by 4 and dividing by 4 canceled out and put us back to where we started. So we've done the powers. What is the inverse of a power? Right. If I take 9 squared, I'm going to get 81. If I want to take that 81 and get back to 9, I need to square root it. The square root of 81 is 9. Now I do have to be careful. If I punch in second square root of 81, calculator is going to tell me 9. But remember that square root is an inverse. It's reversing this operation here. So the square root of 81 equals 9 because 9 squared equals 81. However, is there another number squared that would give me 81? Negative 9. Negative 9 squared also gives me 81. So up here, the square root of 81 is 9 or negative 9. Both of those are potential answers. Now, for most of what we're going to do in this class, we're going to take the positive answer when there's two like that. But be aware that both answers are viable. And if you were into like a technical math class or a college algebra class, and you were solving an equation with a square root, it would be important for you to consider both the positive and negative possibilities, because there would be two answers to that equation. What's the square root of 25? 5. Good. What's the square root of negative 25? A lot of people want to say negative 5. But if we try it on the calculator, square root of negative 25, it gives us an error. If I were to square a negative 5, it would be a positive 25. Remember, the square root of 25 is 5 or negative 5. Both of those are square roots of 25. So they can't be the square root of a negative 25. We cannot take the square root of a negative number. Now, I say that a little bit tongue-in-cheek because if you were to take a college algebra class, you would hit this problem like this, and they define a way to make it work. You don't have to write this part down because I'll never test you on it. But what they define in a college algebra class is that the square root of negative 1 is an imaginary number. So they say the letter I is the square root of negative 1. If I have something like the square root of 36, I can split that up. 36 is 4 times 9, correct? So I can split that up in the square root of 4 times the square root of 9. What's the square root of 4? 2, and what's the square root of 9? 3. That multiplies to make 6. Well, the square root of 36, we all know, is 6. So that works. So what they would do then for the square root of 25, or negative 25, is they'd break that up into the square root of 25 times negative 1. So then it would be the square root of 25 times the square root of negative 1. What's the square root of 25? 5. And the square root of negative 1 is I. So it's 5 times I, or 5i. We're not going to do that in here. But if you go on to the next step, like I said, a college algebra class, in fact, even if it was just an intermediate algebra class, you would see that those imaginary numbers. If you were to go to a bachelor's degree, you'd have to take a college algebra and a statistics course at some point. For that class, it depends on what point in the course you're at, you would not be able to do that. You'd have to put it out as in terms of I. Now, there's a whole branch of algebra that deals with those imaginary numbers. So that'd be like a 2-week section of a college algebra course, how to deal with I, which we're not going to get into, but you treat it almost like a variable. Well, it's weird because there's sometimes you can. Like if I have 3i times 7i, just like if I have 3x times 7x, I do 3 times 3 is 21. X times x is x squared. Do the same thing here. 3 times 3 is 21. I times I is I squared, or negative 1. Remember, I is the square root of negative 1, so you square it, you get negative 1. So that's negative 21. So the i's disappeared there. So I don't want to get too far into it, but you can see it's a whole different section of algebra on its own. Well, it's kind of the sadism of mathematicians of here's something that couldn't be done, so we made up a whole field of algebra to explain how it could be done. We're not going to get into that here. But like I said, for most bachelor's programs, you would need to take at least an intermediate algebra course and a statistics class. Okay. What if I have the square root of 4 over 25? Well, let's back up. What if I have 3/7 squared? Well, that's just 3/7 times 3/7, correct? And when I multiply fractions, I just multiply numerators. I multiply the counts. 3 times 3 is 9. And I multiply the names. 7 times 7 is 49. That is the same as 3 squared over 7 squared. When I take a fraction to a power, I can split it up and I can do the power on the numerator and the power on the denominator. So if I have 2/5 to the power of 6, I can do 2 to the power of 6 over 5 to the power of 6. 2 to the power of 6 is 64. 5 to the power of 6 is 15,625. So now back up here. The square root of 4 over 25 is saying what number squared equals 4/25. Well, 2 squared equals 4, and 5 squared equals 25. So it would be 2/5 squared. If we look at that, we can take that square root, just like we took this squared and split it up, or this 6th power and split it up. I can take that square root and split it up. I can take the square root of 4/25 and do the square root of the numerator over the square root of the denominator. Square root of 4 is 2, square root of 25 is 5. No, just 2/5. So if I want the square root of 49 over 81, I can split it up into the square root of 49 over the square root of 81. What's the square root of 49? What's the square root of 81? 9. Very good. Square root of the numerator and the square root of the denominator. Yep, that's all it comes out to be. What's the square root of x squared? X, right? Squared and square root reverse each other. So it just cancels out and we get just x. What would be the square root of x to the 6th? Well, it's asking us what number squared equals x to the 6th. There we go. If it's your x to the 3rd to the power of 6, remember when we do a power of a power, we multiply. 3 times 2 makes 6. X to the 6th. That's exactly it. When we square root a variable with a power, we're dividing the power by 2. So that's x to the 3rd. If I have the square root of x to the 8th, y to the 14th, I can do each variable separately. It would be x to the 4th and y to the 7th. Five to the power of 3 equals 125. How do I get from 125 back to 5? It's not going to be a square root, it's going to be a cubed root. That little 3 in front here, it's called an index. And that's saying is that this is not just a regular square root. It's saying this is a cubed root, which means it's supposed to reverse a third power. So the cubed root of 125 equals 5 because 5 to the third power is 125. So of course this is going to be called a fourth root. The fourth root of 81 is asking what number to the power of 4 equals 81. Well, we found this, we found it before. It's 3 to the power of 4 is 81. On your calculators, yours will probably work a little different than mine. Wherever your caret key is or your power key like that, above it is generally a key that looks like this. It has an X or an N there. It's the X root key. To do this, you would type in the 4, press that key for the X root, and then type in the 81. My calculator is a little different. I've got to do 4, go to the math menu, and get my X root, and then type in the 81. And I get 3 for my result. So what's this asking? Exactly. What number to the fifth power is 3,125? How do we find it? We have to do a fifth root. 5, I got to go into my roots. 3125. We've done this one the other way enough, we should know that that is 5 to the fifth power. Well, looking at these last two examples I did here, one of them is correct, and one of them is only half correct. One of them has only the answer we found. The other one has a second answer. Can anybody tell me which one of these has a second possible answer? Remember, this is saying what number to the fourth power is 81? What number to the fifth power is 3,125? Is there any other number to the fifth power that would be 3,125? No, but there is another number other than 3. 3 to the fourth is 81. What's the other number? Negative 3. Because this is an even power, negative 3 to the power of 4 is also 81. 3 to the fourth is 81. But negative 3 to the fourth. Not a positive power, but a even power. So if it's an even root like this, it's 3 or negative 3. It has two possible answers. An odd root like that only has that one answer, a 5. Now, the opposite side of that is what if I want to take the fourth root of, oh, let's see here, negative 625. If I punch that in my calculator, fourth root, negative 625, what's this going to tell me? It's going to tell me I did a bad thing. Give me error. Why did it do that? Well, because it's asking what number to the fourth power is a negative 625. Well, we know anything to the fourth power is going to be positive because it's an even power. So there is nothing that we can take to the fourth power and get a negative answer. Now again, you get into a college algebra class, they'll talk a little bit differently about those. But no. Well, I might put something like that on a test, but you'd have to say, oh, can't do it. You can't take the even root of a negative. But a fifth root, if I ask you for the fifth root of a negative 32, can that be done? It's asking what number to the power of 5 is a negative 32. Can I take something to the power of 5 and get a negative result? Yes, I can. Fifth root of negative 32 is negative 2. Did you fifth root or square root? Okay. Did you get to work? Okay. So an even root, we cannot do an even root of a negative number, but an odd root, we can. We can do a fifth root or a third root or a seventh root of a negative number, because an odd power, we can get a negative result. Let's look at variables. The third root of x to the sixth is asking us what number to the third power is x to the sixth. Well, I'm assuming I'm going to put x to some sort of a power here. If I knew what number this is, what would I do to it to make it to the third power? I would multiply this times the 3, correct? Well, what times 3 makes 6? 2. This has to be x squared. So if you look what's going on here, when we do a third root of a variable, we're just dividing the powers. 6 divided by 3 is 2. That's x to the second. If I had a sixth root, say, the sixth root of x to the 30th, same thing's going to happen. I'm going to divide the powers. What's 30 divided by 6? 5. Very good. Because x to the fifth to the power of 6 is going to equal x to the 30th. That sixth root has to reverse it. So what is the fourth root of x to the 24th, y to the 12th? Well, what's the fourth root of x to the 24th? X to the 6. Good. 24 divided by 4 makes 6. And y to the third. Y to the 12th. 12 divided by 4 makes 3. And we might have the fifth root of 243, x to the 40th, y to the 65th. Now, when we do this, do we take 243 divided by 5? No. We actually have to do the fifth root of 243. So fifth root of 243 should be 3. Then we do the variables. It'll be x to the 40 divided by 5 is 8. And then y to the 65 divided by 5 is 13. Very good.
Don't divide the first number.
Correct. It's just like if we had 5x to the third, y to the 8th, to the power of 4. We actually do take the 5 to the 4th power, which is 625. That's 5 times 5 times 5 times 5. But the variables, we just multiply the powers. Y to the third to the power of 4, or sorry, x to the third to the power of 4, just 3 times 4 is x to the 12th. Y to the 8th to the power of 4, 8 times 4 is 32, so it's y to the 32. So we do a root, it's the same way. The fourth root of 625, x to the 12th, y to the 32nd. We actually have to do the root of the 625. The fourth root of 625 is 5. And then we just divide the powers on the variables. 12 divided by 4 is 3, so x to the third. 32 divided by 4 is 8, so y to the 8th. Excuse me. Can this be done? I've got a negative in there. Can I do this? Yes. Why? It's an odd index. A fifth root. Since it's an odd root, I can go ahead and do that. What is the fifth root of 1,024? Negative 4. Very good. How about the fifth root of x to the 15th? X to the third. And the fifth root of y to the 20th? Y to the 4th. It is time for our break. So let's take our break. We'll come back at about 9:29 or 9:30 and we'll go from there.